Now we shall discuss the next theorem in the section closed sets. And now I will state the theorem. There are three parts of this theorem. This is a very lengthy theorem. Let f be a one-to-one functions. Let f be a one-to-one function. Let f be a one-to-one function from a metric space M1, from a metric space M1 onto a metric space M2. The explanation is, that is, M2 F is a one-to-one correspondence. Already we discussed this in the first chapter. F is a one-to-one correspondence. CORRES, one-to-one correspondence between M1 and M2. When a function is both one-to-one and onto between two metric spaces, then the function is called as a one-to-one correspondence. Then, if there exists a one-to-one correspondence between two metric spaces, then if f has any one of the following properties, if f has any one of the following properties, then it has them all. That is, there are going to be three conditions, and if any one is satisfied, then it satisfies the others. So all three are equivalent. Both f and f inverse are continuous. So both f and f dash are continuous. B, the set G in M1 is open. It's open set if and only if its image, say f of g, its image f of g in M2 is open. This is statement B. Statement C, same like G, is closed set F. The set F contained in M1 is closed if and only if its image f of f, which is a subset of M2, is closed. So what we have to prove is, so the meaning is, if f has any one of the following properties, it has them all. The meaning is, this part is the assumption we have to make, that is f is 1 2 and on 2, and that is common for all the three statements. First what we will do is, first we will assume a is true, then we will prove that b is true. Then we will assume b is true, then we will prove that c is true. Finally we will assume c is true, then we will prove that a is true. That is, if any one of this property is true, then automatically the other two properties are true. So that is what we have to prove. So this is the way we are going to prove. So first, the proof of this theorem, it is of this type. We are going to first prove that the implication A implies B. This is what we are going to prove first. So what we are going to assume, but for all the three statements, this is true. That is, f is 1 to 1 and on 2. That is, f2 is a 1 to 1 correspondence is a common assumption. So now we are going to start proving the relationship A. If A is true, then B is true. So what is the assumption we are going to make here, you see? Let us assume that, so what is the first statement? We are going to assume that both the function f and f inverse are continuous. Let us assume that both f and f inverse are continuous. This is the assumption. That is, A is true, we have assumed. So we are going to prove that B is true. Now, so the common assumption is, since f is 1 to 1 as well as on 2. Whenever a function is both 1 to and on 2, the inverse function is well defined and exists. So that's what we are going to do. Since f is 1 to and on 2, f inverse is well defined. So f inverse exists. Now what we are going to prove is statement B is true. That is, first we will assume that G is open in M1. We will prove that the image is open in M2. Then we will assume that f of G is open in M2. Then the corresponding inverse image G is open in M1. So for the same assumption A, we are going to prove B, which in turn is we are going to prove the necessary and sufficient. So now we assume that f is both f and f inverse are continuous. So f is 1 to and on 2, therefore f inverse is well defined. Now, since f inverse is a continuous function, f inverse is a continuous function, this implies that f inverse of G is nothing but f of G is open in. I will tell what is the result we are going to use it. I will put it here something star. This result only we are going to use it, that I will tell you. Already we just discussed this one in open sets section. F is continuous if and only if f inverse of G is open in M2 whenever G is open in, f inverse of G is open in M1 whenever G is open in M2. It is, suppose you take, this is a metric space M1, this is the metric space M2. So what does it says is, the function is continuous if and only whenever we take one open set in G here, the inverse image under the mapping. So this is f inverse of G. This is also open. If G is open, then f inverse of G is also open. This is a theorem, already we proved. So the same theorem we are going to use it, but the only change is, instead of f in the function f, we are going to use f inverse. See, for this theorem, we know that f is a function from, for this theorem, f is a function from M1 metric space to M2 metric space. But what about F inverse? F inverse is also what we assumed here is both Fn and F inverse as continuous. See, F inverse is a function from M2 to M1. So to avoid confusion, we will write like this. This is M2, this is M1, and our function F inverse is like this. So if we are confused, if we put F inverse as G. So now F inverse is continuous, we have assumed. So by this theorem, suppose we take any open set here, G in M1, the inverse image, that is nothing but G inverse of G is also open. This is by this theorem. So what is G? G is nothing but F inverse. So this is nothing but F inverse of G. That is what I have written here. So this big explanation you can hide, but we are going to use this theorem. So that is what's happening. Since F inverse is continuous, F inverse, the inverse image of G is open in what? M2. Whenever G is open in M1, very careful, you have to be there. That's why I draw this. Where G is here, you can see G is open in M1. So by this theorem, since F inverse is continuous, we got this result. That is finally what we got. This F of G is open in M2. G is open in M2. Now, F inverse of G, what is this? Finally what we proved is, you see here, that is F of G. That is F of G is open in M2, we have proved it. So now I am going to start with this. F of G is open in M2 and F is continuous. This implies that, you can see we are going to use this again, the same this result only, this star. Here also I am going to use this result star. I will just explain here. So here this is again M1, this is M2. F is a continuous function from M1 to M2, and just now we proved that this is one thing. No? So what is this? This is F of G. F of G is open. Just now we proved it. Open in M2. So now, as per this star result, the inverse image of this set under in. So this is nothing. Suppose this is F of G. Already I marked it. No? Sorry. Already I marked it. This is F of G. What is the inverse image of this? So this is nothing but F inverse of F of G. That is nothing but G. This is nothing but G. So that is what we are going to do. See, F of G is open in M2 and F is continuous. So by the result star, F inverse of F of G. This is nothing but G is open in M1. Therefore, hence, that is what we proved. Hence, G is open in M1. So, see, one part of the A implies B is over. Suppose we assumed that A is true, then we proved one part of this. We assumed that G is open. So now I just explain again here. See, so we assume that f and f inverse are continuous. Now we have to prove that the statement B is true. B is both necessary and sufficient part we have to prove. So now first we assume that G is open, then we will prove that f of G is also open. Then we will assume that f of G is open, then we will prove that G is open. So first thing is, we assume that G is open. We assume that G is open. If G is open, we assume that we proved that using this star result, we proved that f of G is open. So one part is over. Now next we assume that f of G is open. So sorry, this is nowhere linked with this. This f of G is over. Okay, now this is if we can prove. If f of G is open in M2 and f is continuous, already is assumed. So this implies that just now I explained G is open in M1. So we proved the both the necessary and sufficient part of B. It is, first we assumed that G is open in M1. We proved that f of G is open in M2. Then we assumed that here if f of G is open, we proved that G is open. So this completes the proof of A implies B. So if A is true, we proved that B is also true. The thing is, B is having both necessary and sufficient part. That's why we have to first assume this part and prove this one. Then we have to assume this part and prove this one. Now, next we are going to go for proving if B is true, then it will imply the truth of C. So this is what we are going to prove. So now we are going to assume that B is true and prove that C is true. What is C? Same thing for closed set we have to do. That is C. So for proving B, we are going to assume that B is true. Now let us assume that this is also contains necessary as well as sufficient part. That is, first we will assume that f is closed, then we will prove that f of f is closed. Then we will assume that f of f is closed, then we will prove capital F is closed. Assuming that the statement B is true. So let we assume that let f be a closed set in M1. So which implies double star is, I am going to write the result, which implies M1 minus F, that is the complement of F in M1 is open in M1. So this result already we proved it. G is open in M1 implies the complement is closed. Like this one theorem is there, that result only we are using here. Okay, that result implies F minus F is open in M1. By the assumption of B, that is B is assumed, by assumption of B, M1 minus F, that is the complement of F, is open in M1 if and only if f of M1 minus F is open in M2. So that is the assumption of B. What is the assumption? B says whenever you take an open set in M1, the image of that open set is also open. So now, just now we proved that this is an open set in M1. Therefore, as per the assumption of B, the image of this, that is f of M1 minus F, is also open in M2. So this double implies, that is if and only if this can be written as f of M1 minus F. This can be written as f of M1 minus f of F. because the function is both one-to-one and onto, this is possible. So what is f of m1? That is a range, but here range is equals to codomain because the function is one-to-one and onto. Therefore, this is nothing but m2 difference f of f. M2 difference f of f. So from this we continue. So this is open in M2. So this is same as what? This. So this is open in M2. I am just copying the same statement, but only thing is this one I have changed it. Okay. So what is the final conclusion? M1 difference f is open in M1 if and only if M2 difference f is open in M2. M2 difference f of f is open in M2. This implies that what is the complement of this in M2? F of f. F of f is closed in M2. This is by star. Sorry, double star. This result. This result. The same thing. Can you here put? Another one result also is there. F of f is closed in M1, then the complement is open. Both open, we can put that same double star. So this is open, then its complement, that is f of f, is closed in M2. This is what we wish to prove. The necessary part of C. What is the necessary part of C? We assume that f is a closed set, then we proved that f of f is also closed. So we prove. See, first we assumed that in the beginning f is a closed set in M1. Finally we proved that f, the image of that one, is also closed. So now we don't want to prove the sufficient part because everything here is double implies. Here. The same thing if we come from bottom, so this will prove the sufficient part. Okay. So now we will prove the statement finally. This is M2 and this is also different because converse also we have proved it in that statement. So overall all the statements are related by double implications. So we proved the statement B implies C. Now finally the proof of C implies A. Proof of C implies A. We shall write like this: proof of B implies C. Proof of A implies B. So now what we are going to prove is let us assume that B is true, then we will prove that both A, F and F inverse are continuous. Now let us assume that F be a closed set in M1, which implies that F inverse of f, this is nothing but f of f is closed in M2, which implies that f inverse is continuous on M2. See, just now how we got this result is, see, previous to this theorem we have proved it. We have proved one result, that f is a function from m1 to m2 and f is continuous if and only if the inverse image of any closed set is closed in M2 whenever f is closed in, sorry, this is M1, whenever f is closed in M2. That is, little bit graph work I will do it. This theorem I am explaining. So be very careful with the function f and f inverse. F is a function from here to here, m1 to m2, and f is continuous if and only if whenever we take any closed set in m2, the inverse image is also closed in m1. If this is closed, and it's if and only if statement. If it's continuous, this property is true. If this property is true, then f is continuous. So now the same theorem we are going to apply for the function f inverse. So that is the thing. So now what happens is, f inverse is a function always from m2 to m1. So now we take one closed set here, m1. So what is the inverse image of this function f inverse under inverse image of this one under f inverse? So that is like this is, this is nothing but f inverse of, sorry, it should not write like this. It's nothing but the f inverse of g. But this is nothing but f of g. If f is closed, then f of g is also closed. So that is sorry, f of f. Sorry. F of the same theorem only, but we applied for the what the function f inverse. So that's what. So you can put a star for this result and put it here. But again star. Simply you can use some other symbol here. Okay. So by using this result, since f is closed in M1, you can see the graph. Here you see f is closed in M1, then f of f is closed in M2. That's all. So this is what if this is satisfied, then as per this theorem, which is if and only if statement, which implies that f inverse is continuous on M2. So f inverse is continuous on M2. Okay. So by this theorem we proved that f inverse is continuous. So now we are going to prove that f is continuous. If I prove that one, A is over. Now let us assume that f of e is closed in. I am going to use this result directly here. Okay. So instead of f, I use the word e. Let us assume that f of e is closed in M2. Assume that f of e is closed in M2, then E is closed in M1 by the assumption of C. So what is C says? We assume that C is true. So what is C says? Uh, Whenever we take any closed set in M1, the image is also closed. And if you take the any set closed in M2, the corresponding inverse image is also closed. So this is what C statement says. So we are assuming C is true. So that f of e is closed in M2. If f of e is closed in M2, something like this. Suppose E, this is E, this is f of E under the map F. So what is the assumption C says? If this is closed, if this is closed, then E is also closed, and the other way is also true. So we assume that f of E is closed in M2, then E is also closed in M1 because C is true. Our aim is to prove that F is continuous. Already we proved F inverse is continuous. Okay, now but this set E can be written as F inverse of f of E. This is using the function properties. This is we know that these things. Hence for f of E closed in M2, the inverse image of this f of E is nothing but E is closed in M1. Before this theorem we proved one big theorem. What is that? Same like for open sets, F is continuous if and only if f of f is closed in M2, f inverse of f is closed in M2 whenever f is f is closed in M2. This is the result we proved before this theorem. So using this result only we are going to come to the conclusion. Now what we have taken is, we have taken that f of E is closed in M2, then so what we proved here is that is for the function f inverse. In place of f, we use the function f inverse. See, just again, just here. This is so let us assume that f of E is closed in M2. Then E is closed in M1 because the assumption of C. What does C says? F of and so so what we have proved is we assume that C is true, and we proved that both F and F inverse are continuous. So from this, what you can conclusion is, so what is the conclusion is, yes. So we assume that f of e is closed in M2, then e is closed in M1 by the assumption of C. But e can be written as f inverse of f of e. So hence for f of e closed in M2, the inverse image of f of e is equal to e is closed in M1. So what you can tell about f inverse? F inverse is a closed set in M1. F inverse is a continuous function. So that is what we have proved here. First we proved that so just a second. This is a proof of C implies A. So first what we assumed is, we assume that C is true. So we are going to prove A is true. So what is this? We assume that, what is C? C is, if F is closed, then the image is also closed. So we assume that F is closed. So by this result, F is closed in M1. So F inverse of F is nothing but F of F is closed in M2. This is by this result. This 3 star is there, no? This result. Because this condition is true, if this condition is true, then F is continuous. Here in place of F, we are going to use F inverse. That is the thing. So first we proved that F inverse is continuous. See here. So first we proved that F inverse is continuous. Using the result, this result. Okay. Now second, we have to prove that the function f is continuous. So now again we are going to use the result C. That is, that C is if and only if statement. So now we are going to assume that f of e is closed in M2. Therefore, according to C, f is that e is closed in M1. So that is by 3. That is a if and only if statement. But our aim here is, first already we proved that f inverse is continuous. Now we have to prove that f is continuous. Then only A is completed. So now, so this is the assumption of statement C. Now this this element, this set E can be written as like this: f inverse of f of E. This is known for, from the properties functions. Hence, so we assume that f of E is closed. Hence, for f of E closed in M2, so what happens is the inverse image of this function f of E is nothing but E is closed in M1. So again by this theorem, this is a theorem for f is continuous. In general, a function f is continuous if and only if the inverse image of closed set is also closed whenever f is closed in the codomain. So the inverse image of this is nothing but E is closed in M1. So this implies that the function f is continuous on M1. So the last result, we used this theorem. So by using this theorem, we got that f is continuous. So by the assumption of C, if this is closed, then the corresponding E is also closed by the assumption of C. So now we have to prove that f is continuous. So for f is continuous, if you take the domain and codomain like this, if you take any closed set in the codomain, the inverse image also must be closed. If that is the case, that is what this theorem, this result says. Okay. So now we are going to use this result to prove that f is continuous. So now already we showed, we have assumed that if f of e is continuous, e is also, sorry, f of e is closed, then e is also closed. We have proved it, that is by assumption of C. Now simply we are going to use this statement. This is very important. This e can be written as f inverse of f of e, where f of e is closed, already we assumed in C. So, and e is also closed by the assumption of C. So what we get, for any closed set in the codomain, the inverse image is also closed. So this is the theorem we used it. And what it says, if this is true, then the function is continuous. So already we proved that f inverse is continuous. Now we prove f is continuous. So A is proved. So this implies, this completes the proof of C implies A, and hence the theorem. Hence the theorem. So this completes the proof of the theorem. So now this completes the proof of the theorem. Now we have some 2-3 definitions that I will write now. That comes to the end of the unit, this section, closed sets. Definition: if f has any one and hence all of the properties A to C in the previous theorem, just you can refer it. 3. We call that the function f a homeomorphism. Not homomorphism, homeomorphism from M1 on to M2. So if there exists a function between M1 and M2 which satisfies the conditions A to C, then the function is called as a homeomorphism. And if the homeomorphism exists between two sets M1 and M2, then we say that if a homeomorphism from M1 on to M2 exists, we say that M1 and M2 are homeomorphic to each other. So there are a lot of examples. That is, from the previous theorem, what you can say is, if f is both one-to-one, on-to, and continuous, if the three things are true, then we can tell that this function is homeomorphism. That also you can use it, or you can use using the properties 1 to 3. Because if any one is true, the other things are true automatically. So you can keep in mind the function is one-to-one, on-to, and continuous. Then the function is a homeomorphism. This we can keep in mind. Some small examples are there. Just examples, you can verify it, that there exists a function between these two sets which is one-to-one, on-to, and homeomorphism. So what are the things is, the set 0, 1, here the metric space M2 is 0, 2. There is a function between M1 and M2 that is defined by f of x equals to 2x, and you can check that this function is one-to-one, onto, and continuous. Definitely it is continuous function because 2x is a continuous function. For every value of x, the function value exists. So continuous, one-to-one, onto. Therefore this exists a homeomorphism, and we say that this is a homeomorphism function between these two metric spaces m1 and m2. Both the metric spaces the metrics are absolute value function, absolute value metric, and so these two sets we call it as homeomorphic to each other. This is an example. Another example is the m1. M1 is 0, infinity. M2 is set of all real numbers, and there exists a function from this one to this one, and the function is f of x equals to log x. You can check that this is both one-to-one, onto, and continuous. You can check the graph also, it is continuous, one-to-one as well as onto. Therefore, I can say that both m1 and m2 are homeomorphic to each other. So, the final definition we are going to see is called dense subset. Dense. What is called as a dense set in a metric space. Let M be any metric space. Let M be any metric space. The subset A of M is said to be dense. Said to be dense. Said to be dense in M if it satisfies these conditions. That is, the closure of A will be equal to the full space M. That is, A is dense in M if every point in M is a limit point of A. Very good examples are set of all rational numbers. Rational numbers is a dense subset. The set A of rationals in R is a dense set. That is, set of all rationals denoted by Q, then the Q bar will be equals to the closure of Q is nothing but the entire real line. This is because every irrational number is the limit of a sequence of rationals. So, because the full real set is divided into two. The one is rationals, the other one is irrational, the complement. So, because if you take every irrational number is here, for every irrational number there exists a sequence of rational numbers for which this irrational number is the limit, but this limit is not in Q. So what happens is, so whatever element is there, a sequence is there in Q that has a limit in Q dash, that is irrational number. So what happens, the set of all limit points of Q is nothing but the entire uh, what real line. Apart from Q, all the limit points are belonging to Q dash. That is the irrational number. So that is why Q is dense in R. So the other example, this is the first one. The second example, RD. You consider the metric space RD. RD has no dense set. Has no dense set except the full space RD. No other space satisfies this dense property. That is a subset whose closure will be equal to the full space. Why? Why is this happening for RD? Because if for any subset A, it's a subset of RD, then the closure of A is equals to A. Because already we proved some in the open sets, we proved that every subset of RD is open. So what happens is, in RD already we have the result. Why we are getting A bar equals to the closure of A equal to A means, see, already we have proved that every subset, whatever subset of RD you take is open. Whatever subset we take, it is open. So here A, which is a subset of RD, which implies that by this theorem A is open. If A is open, another one result we have proved, the complement of this RD minus A is closed. That is, suppose this is RD and suppose this is the subset A, this is RD minus A, the difference, the complement. So now, just now you showed that this is open. So R minus D is closed. So R minus D is closed means, what is the meaning? All the limit points of this set is inside this one. So A should be also closed. So A should have its own limit points, because the limit points cannot be here, because RD is closed. All the limit points of this is inside RD minus A itself. So here every subset of RD is open. This is the important result. So whatever subset we take, it should be open. So now what we do, A is a subset of RD, therefore it should be open. So another one result we using, some theorem is there. You have to cite that theorem, which implies the complement is closed. But this is also what? A subset of RD. So as per this one, again this RD minus A is what? Open. You have to use this theorem here. This theorem you have to cite it here. Okay. So by that theorem, see here, simply write like this. Now RD minus A is closed. RD difference A is closed, and I do not use the word closed. Now RD minus A is a subset of RD, and hence it is open by this theorem, the same theorem. So if this set is open, which implies the complement of this is nothing but A, is closed. If a set is closed, what is the meaning? That is A equals to A closure. So this is not equal to what? A and A is equal to A closure, but this is not equal to the big space R. Therefore A is not dense in RD. Like this we can complete the proof of this. If they ask in the examination, prove that there exists no dense subset in RD, you have to give like this explanation. So this completes this section, closed set, that is section 5.5.